So it'll be a working session. I'll be asking you guys questions. Feel free to lift your hand up and ask me any questions. As I mentioned, we'll talk a little bit about the generic steps for any data science project. Taking your first glances at the data, what things are you looking for, what things to look out for, what is the focus point. Then we talk about data set building, which is really important. So how much data, is it balanced? Again, kind of what are you looking for the first time and how do you iterate over it? Then we'll go into, once you have your data sets and you understand your data, how do you begin picking a model, right? There's so many models that do so many different things, like how do you start that process? And then once you pick a couple models, how do you evaluate it? How do you know that it's doing a good job? What are some of the basic metrics? And then at the end, we'll say, you know, if we wanted to use AutoML instead of our own model selection, what would that look like? How does a project look like with AutoML? What places can be replaced by? Like, what does AutoML do for data scientists? What if it doesn't do? There's a lot of misconceptions thinking that AutoML is just going to replace data scientists. So I wanted to kind of just write this story and just showcase kind of what are some important things it can do. So data exploration. So before we go into this, the use case that I've prepared today, or that's been prepared today, is on the medical industry. They have, the business case is not really important for this presentation, but readmissions in hospitals are very expensive. So if I broke my arm and I go to a hospital and I get fixed and I come back 2 or 3 days later to get it fixed again because it wasn't fixed right or it wasn't all diagnosed, it's really expensive. When it comes to diabetics, this case is a case study on how to predict readmissions for diabetic patients under 30 days. So there was a big problem where diabetic patients would go to a hospital, they'd come out, and then before 30 days they'd go back to the hospital because they'd have either new symptoms or they were maldiagnosed. So this case study is how do we predict which of these patients will come back to the hospital, and if you can get an accurate model on that, how can you notify the doctor that the person that you're helping will probably come back to the hospital, so like maybe do some extra checks to make sure it doesn't happen. The data set we're going to use, and I'm going to demo it in a second, is public data sets, so there's nothing private on it. This is one of the many data sets. It's an older one from 1998 to 2008. It's basically hospital admissions. So folks come in, they have an ID, they have blood pressure, they have certain information about them. It's been scrubbed, so there's no names, but there's sex, race, age, and a couple other things that we'll look at in the data. So this is public information, you can look at it. And what we'll do is we'll explore kind of first glances. If you guys were doing this problem or you guys wanted to try to do this problem, you open the data set, we're going to see it in a second, and we're going to start deciding like, how do we start using it? Like, where do we go from there? Is there any questions so far? No? Okay, so data exploration, I'll go with theory first and then we'll do a real life example. Data exploration, there's a lot of things we're looking at. The first one is when you take depending on the size of the data, sometimes it doesn't fit in an Excel file and you have to use tools like Spark or something. But assuming this is just something under maybe a gigabyte or a couple hundred megabytes, you take a look at the data. Usually it's going to be in CSV format, doesn't always have to be. And you're looking for, so you got a bunch of columns, right? You got maybe 50, 60 columns, you got maybe 100,000 rows, 200,000 rows, whatever it is. And you're trying to look for, the first thing you take a glance at, null values, columns that you think are important. Is it complete? If it's complete, is it broken into things that make sense? Is there something that, a lot of times it maps to another table. So first one is like assess data quality, and I've left that bland and vague because it is kind of a vague thing to do. You're just kind of eyeballing it and you're just looking for potential problems. Like I noticed that this column is mainly empty. I noticed that there's nulls in the data. I noticed that it's a number numeric field like age, but it's actually a string, right? It's a string in the column, not a number. That's going to create problems later on. That's something that we'll have to manipulate. And then once you kind of take a look at it, most of the public data sets have documentation on what it is you're looking at, which is really helpful. You start doing your initial kind of feature list. So this looks like, in our case, we're looking at readmission of diabetic patients. So if I'm looking at the data set, things like age is probably going to be important. Things like race are going to be important. Different genetic gene pools have different discrepancies with diabetes. Things like, well, we'll look at it, but like a couple of things that you're going to look at, okay, I think these are going to be important features. You have no way to validate that until we start running the models. But you're going to start picking up a few. And one of the biggest mistakes I see in folks when they're starting out is they pick way too many to start with. And then you're spending 100% of your time doing feature engineering, data manipulation, and you haven't built a model. So you try to pick up a few of the big ones, try to work with it. Usually your model's going to fail right away, it's not going to do well. You come back, look at the data, see why, we'll like have a discussion on what things we're trying to do. Maybe add some more features, and now maybe you might change your model. And this is kind of an iterative process. And the more times you do this, the more things you start noticing, which models work, what features didn't work, what types of data were working with you, weren't working with you. So we'll take a look at that. And the third one is metadata. So this is, and we'll see this in this data set as well. For example, when you get discharged from the hospital, you'll get discharged off various different codes. So maybe you broke your arm, you got a cast, the doctor's complete. So they'll have a discharge code that represents the doctor diagnosed you. Sometimes they'll discharge you, but just treat your symptoms. So you come in with a huge headache, they've given you Advil, I'm not sure, I'm not a doctor. Or they've gotten rid of your headache and they sent you home, but they know they haven't gotten to the root of the problem. They might put another discharge code there, and that's going to have another table that code kind of maps to. So that's kind of the understanding the metadata of the data, as well as the relationships between the features. How does one correlate from one to the other? So if I'm doing, the example that you always see is predicting house prices. If one of your features is the square footage of your place, and another feature that you've decided is important is how many bathrooms it has, there's going to be some correlation with as big as when the square footage gets bigger, you're probably going to start having more bathrooms. And depending on how tightly coupled that data is, it might not be worth to even have that second feature. So you do things like correlation understanding and correlation analysis on your features, see how correlated they are one to the other. But that's kind of the general. So let's take a look. Let's take a look at the data. This is just a Jupyter notebook. Let's see if I can zoom in. Can you guys see okay back there? Okay, so. Okay. So this is just importing the data. This is nothing to use. So all I do here, and if you're not familiar with the code, that's totally fine. All I'm doing here is just taking the CSV file that was from that public library, turning it quickly into a Panda data frame, which just allows me to look at things like counts, look at, we'll see all the things that we're going to do with it in a second, but this allows me to manipulate the data, start doing some quick counts and sums and seeing what the data looks like. I don't know why it's jumping. Okay, so here, the first thing I did was an info. Sorry, I'll try to scroll a little more delicately. So info will just tell me all the columns. So I look at 50 columns, and it'll give me a very basic report on just what data type is in it. Objects can be something like strings, can be some kind of other more complicated object. But I'm looking at it, I see objects in 64, which are ints, those are numbers. So that's my first thing, and then I'm looking at the column names. Most of them I don't understand. Like some of that, insulin is probably an important thing for anyone that has diabetes. That might be interesting. And then right here is readmitted. So when I went through the documentation, I noticed that the readmitted column is telling me whether this patient was readmitted to the hospital. This is what we're trying to predict. So this is the label in our case. And we'll talk a little bit more about what that means, but that's going to be an extremely important column to get right and to get in the right format. So go down. So the head function here is just all it's doing is taking the top 5 rows and just displaying it to me. So I haven't done anything with the CSV file. I could have loaded it in Excel at this point, but taking a look around, right, there's 50 columns. So if I looks like the encounter ID is the unique identifier for the admission. So every time you go to the hospital, you get another Admission, probably not that important for me. Race is, I look here, at least the 5 rows, which is Caucasian, African American. That's going to be an important field. It's in string format. It's going to tell me that I'm going to have to do some more work to get that usable by the model. Gender, male, female, that's going to be an important format. And age. So this is where you can start to get a little annoyed at some data sets. So age is as a string format in this discrete. So age is a number that doesn't need to be discrete, right? You're either 17 or you're 15 or whatnot. But they decided for whatever reason that they want to have these kind of discrete bands of age. So 0 to 10 is all one bucket, 10 to 20, 20 to 30, and so forth. That might produce some problems on how to get that working. Weight, looks like I have no information on weight, at least on the first 5 columns. Then a whole bunch of stuff that are medical terms that I don't know. And then at the end, readmitted. And this is, again, something that can produce some frustration because readmitted it should be yes or no, but now there's this understanding of over 30, less than 30. So then you dig back through the documentation and you go, okay, so they're separating 2 cases. If you readmit to the hospital before 30 days, and if after. So if you went 2 years later about the same problem, you still get a readmitted of, so it would be yes, but over 30. So the problem set that we're trying to solve is we're trying to predict folks that come back to the hospital under 30 days. So for example, the second row is one guy that probably got maldiagnosed, or maybe there could have been something we could have done in the medical world that would have not brought him back, but he came back in less than 30 days. That's what we're trying to predict. Any questions so far? Okay. So we take a look at the data. We get a decent view of kind of what we're working with. We start seeing some things that we're going to have to put some work on, like string fields, the discrete values. Looks like readmission is got a couple characters, categories. So this is where we start really working on what's called feature engineering. So this is us putting work in to make what the original data set is into actual features that can be used by models. And there's three big genres of this. One is numerical data. So when you're looking at numerical data, let's go back to the example of we want to predict the housing price, right? If I did my correlation between the amount of washrooms in the house and the square footage, and I guessed that, you know what, they're not that correlated. I think the amount of washrooms in a house is an important feature to determine the house price, and that I want to keep the square footage in them together. Well, the square footage of a house ranges vastly, right? You might have a 500 square foot condo, you might have a 2,000 square foot house. That's somewhat of a big range. How much does the number of washrooms range in a house? You're always going to have at least one. You might have two, a 2,000 square foot place, you might have 3, you might have 4. But usually you're probably, depending on the data set you're using, I think we can assume that you're either going to have 1, 2, or 3 washrooms in your data set. So from a model perspective, you got to think to yourself, my square footage is ranging from 500 to 2,000, but my number of washrooms is going from 1 to about 3, right? If you feed that raw data into the model, it's going to inherently learn a lot more or think the square footage difference is much more important than the number of washrooms. And what we're trying to do is we're trying to make it we're not trying to put our bias onto it. We want to regulate these bands and this variance. So we might normalize this numerical data. We might use min-max, z-score, just the average, mean average. We might take these numbers and then convert them to some kind of numbers between 0 and 1, for example, on both sides. So now it's no longer human readable, but the machine or the algorithms won't necessarily weight it heavy, or they might. But that's kind of normalizing numerical data. Dealing with categorical data happens almost all the time, and this is these discrete values I'm talking about. So we'll see an example of one-hot encoding, which is one of the basic methods of dealing with that. But that's you're always going to get strings in your data set, and since we're not building an NLP system to understand, like we don't care if the machine understands what a bathroom is, it just needs to know that it's either has it, doesn't have it, and how many it has. Not that it understands the importance of what that means. And creating new features. So this is, in this data set, for example, the diabetic data set, But I wanted to say, okay, I think that weather is important. I think that depending on the weather outside at the time, it's going to help me predict whether they're going to come back to the hospital. If it's colder, maybe they'll have more symptoms, or maybe things will get worse. I mean, again, this is just a blanket assumption. But if I wanted to add that to my data set, that would be what I would do in feature engineering. I would try to find another source and normalize it and then put it within my data set to add features alongside my data set. So, dealing with categorical data, one-hot encoding. Here's a simple example of how it works. There's, if we're doing color, red, green, yellow, those are string. So imagine we have a string column, and we want to bring it to numbers. Now, does anyone know why we don't want to do just assign red 1, yellow 2, green 3, orange 4, whatever? Does anyone want to take a guess or a stab at why that might not be the easiest way? Yeah.
Let's say you want to count them, or you want to sum them or something. It's
Yeah.
going to mess with some of the numbers.
Yeah, it could help. It could definitely affect how you read it. Yeah.
You also don't want to give the combinatorial assumption that one has more precedence over the other. So 4 is greater than 3, is greater than 2.
Exactly. So 4 is greater than 3. You know, is red necessarily greater than yellow? And the other one is the spacing between it. So if I said red was 1, yellow was 2, and green was 3, now I'm saying that green is twice the distance far away from red or green. And maybe in colors there might be some correlation, but if this was, I don't know, types of chips, right? Like if it was ketchup chips, original Lay's or whatever, the distance between the numbers that you're assigning now have a meaning, and in real life it has no meaning. So that's why we do this kind of one-hot encoding, where what we do is we add another column to our data set. So for example, here we have red or yellow or green, and if that row is red, it has a 1, and it has a 0 for every other color. And so what you're doing to your data set is you're making it go really wide. And depending on how many categories you have, one-hot encoding can make your data too wide sometimes. So if you have thousands of categories, this is not going to work for you. This is going to make it really difficult. There's other kind of discrete value techniques, but this is just kind of in the ballpark of what you can do. And the thing is, you just can't assign a random number because numbers have meaning. And now you're kind of implying all this new meaning to the data that's not there. Any questions? Yep.
When you use ratios, measure extent, the measures
Of the models?
Yeah, like square footage versus.
Are you talking about like model performance?
No, what I'm saying is, like if I want to do a ratio kind of thing. So let's say square footage to the bedrooms.
Sure. Or normalizing, so you're talking about normalizing numerical data. Yeah, so there's things like Z-score, which I think it's the next. Yeah, so here's what you can do to numbers. There's more, but these are kind of the basic ones. You can do the min-max. So you can just say, I'm going to assign 1 to the max number that I see in my data set, 0 to the minimum, and then anything in between, just normalize it between 0 and 1. That doesn't always really work because it's not averaged, right? Z-score is used pretty often. So this is, my mean average of my numbers. So square footage, let's say, if I add all the square footage together and then divide it by how many I have, roughly it's around 850 square feet, right? So then where does that sit? Where does this new value sit within this Z-score? That's a popular technique. Logarithmic is what we use when the numbers have a huge variance. So for example, we're doing fuel amount in a gas station, right? So you're helping a gas company. They want to start doing some modeling on how much gas people buy, right? And you look at your data set, so most people buy from 40 liters to say 120 liters. But then you got these monstrous trucks that come in and they might buy, or you get like those huge trucks that are supposed to transport gas from one petrol station or whatever Shell station to another, and they might use 10,000 liters of gas, right? So you have this, most of your numbers fall in between a range, and then you have these huge outliers that are going to swing your Z-score. You'll have a Z-score of like, it's supposed to be, something small hovering around 0. You'll have Z-scores of 500, 600, 700, right? These outliers are going to destroy you. So you can use something like logarithmic, which is you just it's an asymptote, so you're not going to get hit. So like, these are the decisions you kind of make depending on the variance. And when we go through the data, we do things like min-max. Let's look, yeah, go ahead.
Yeah, well, what's your optimal number of columns for a one-hot encoding?
That's a good question. I kind of use so for example, in this data set, we have 50 columns without doing anything, right? One hot encoding, depending on how many categories we'll see, might turn that from 50 to 80 or to 90. I think that's fine. It really depends on how many categories. If you're doubling your columns because of one category, let's say that 10, 20, 30, so that's 10 categories. If it was 0, I'm assuming that it's not over 100. So that'd be 10 columns. There's not a real science to it, but you just want to take it in perspective of your data set. So I've seen features that are thousands and thousands of columns long. Adding maybe a couple hundred is not going to be that big a deal. Of a feature set that's 50 regularly, if we went up to 150, just do one hot encoding, I would definitely think that we could use another technique. And there are other techniques, but they're around the same ballpark. You just start assigning vectors, and they just don't have to be binary. So yeah, and then also when you go through the modeling evaluation, if your model really starts performing poorly, that's when you always kind of revisit these are all assumptions that you make. You kind of revisit these assumptions, tweak it, run it again, and it's a real big iterative process at the start. Any other questions? Okay. So some tools to normalize numerical data, and then data set building. So once we've kind of started feature engineering, we need to start thinking about how much data we have, how balanced is our data, kind of the macro that we've been kind of microing down to columns and what the values are and all that stuff. But we need to kind of zoom up. We need to think, okay, if I want to train a model data set, the first thing I need is training data, first off. And I'm going to want to separate at least a section for testing that my model never sees, it only predicts, so it's never used in testing. Now, does anyone want to take a stab at why we use validation sets if we have enough data? So, let's say we just had 2, right? Testing training. So you took a wild guess at some models, you took some wild guesses at some features, you took some wild guesses on what encoding types or what z-scores or logarithmics, right? Maybe not so wild, but you took some guesses, and then you get your model and you test it with your test set, and it stops performing, or it's not doing very good. So you go back and rechange it, and then you test it again with that test set, and then you rechange it. What you're doing is you're fixing your parameters, the model types, all that, with what your test results doing, which is creating. So your test results are going to perform well, but that doesn't necessarily mean that's the real world result. Right? So you're starting to have bias. If you're going to use that result set to change your parameters of your models, you're basically fitting it to your test set. So now you want to split it into 3. You want to have your validation test set where you use to run and you're just tuning your parameter, and then you want to have a completely different test set that you hit once or twice, very infrequently, but you don't let that define what your model metrics look like. And that's supposed to be more real-world problems. And there's techniques on designing different types of test sets depending on the balancement. But that's one technique. A lot of the times we find that we just don't have enough good data. So like, how do we go around saying, okay, for example, in this example, we have about 100,000 rows of data. So it's about 100,000 patients that we know that we picked. So it's okay. It's enough to build something, but there's millions and millions and millions of admissions a year, right? So cross-validation allows us to randomly select pieces of our data set to test and train. This is one technique that you can use to help the problem when you don't have enough data to use. Is there any questions on this before I move on? No? Okay. So balanced and unbalanced data sets. So this is quite important. Imagine we were trying to predict a mole being skin cancer, right? So out of all the moles, right, if you look at all the data sets of pictures, how many of those are going to be actual skin cancer? It's going to be, in a real life scenario, quite small, right? So you could have millions and millions and millions of data sets, but your actual amount of data sets that are true, or your true positives, are going to be very small within that. So if your model immediately guessed that everything was not cancer, and this was your data set here. Okay, so if this one was your data set, and you just had a model saying it's not cancer, and you had 10% of your data that was cancer, you'd be 90% accurate, right? So if you feed that data into your model, it's going to totally overthink that everything is not cancer, right? So even a blanket guess is giving you 90% accuracy, and that's why we use the term accuracy very, very loosely. And we'll get into the metrics later. But so what you want to do is you want to train it with a balanced data set. So you don't want to give it 90% one value, 10% the other. You want to actually start trying to give it 50-50, right? But the real world might not have 50-50. So you might have to take a subsection of it, and you start fabricating that data set yourself. So there's a couple techniques depending on what side of the equation you're trying to do. You can do undersampling or oversampling, but essentially it's kind of the same thing. You take sections of the most predominant type of data set, and you try to match it with the other side. So you'll fetch all your cancerous examples in this case, and then you'll fetch as many as you can that make sense. And this is hard because now you have a large amount of data that now you have to sample properly, right? You can't just pick random rows, because you might randomly select a lot of folks that maybe are around a certain age, and now it's like, wow, everyone around this age doesn't have cancer, so now the model is just going to focus on one or two of the features over the other. So you want to have a balanced data set when you do under or oversampling. And you'll learn and you'll see the results when you use that test data set to test it. You'll see if you overfitted or underfitted, and we'll get into kind of those definitions in a little bit. Is there any questions about balancing your data set? Okay. So the fun part, the razzle and dazzle. So after all this work, right? After all this looking at the data, 90% of your time, 75% of your time, now you're trying to figure out what model you're going to use. And this is where AutoML is our friend. So right off the bat, there's two categories of models, supervised and unsupervised. Supervised, which is what we're doing, means that I know the answer to my data set. In this case, I know if they've been readmitted, I know if they've been unreadmitted. Unsupervised are things like, I want to find categories of my data. I want a machine learning model to learn to draw or to play chess or something. There is no immediate right or wrong answer within the data. Is there any questions on supervised, unsupervised? Okay. So within supervised and unsupervised learning, that's the first kind of draw. There's a ton of models we can use, and of all those models we can use, there's another ton of hyperparameters that we can tune, right? And this starts getting into why AutoML can be really powerful, but also really misleading. So I've just put some on the board. They break into many categories, but the two big ones are depending on what you're trying to do. If I'm trying to guess, if I'm trying to say that it is or isn't something, that's categorical, right? So right now I'm trying to say this person either was readmitted 30 days after he was admitted, or he wasn't. It's a binary decision I'm trying to find, so or one of many binary decisions. So that's in the categorical space. If I'm trying to predict the housing price, that's more continuous. I predict this house to be $700,000 or $735,004, whatever. Those are not categorical, right? So that's when we kind of shift our basic models to pick what our output is. Is there any questions on that? We're going to get into some specifics, but that's kind of where the starting piece begins. And then, so when you get here, you've probably really got used to data, you've written a lot of scripts to manipulate the data, you're trying different things out. You spend about 70% of your time in what we've just talked about. And now we're in the business of trying to learn a model and predict it, right? So here's just an example of some code that'll learn the K&N model for what we're talking about, but I'll jump into the notebook in a second. So maybe I'll do that. Let's talk about the evaluation metrics first, and then I'll jump into the code, because throughout the code they use a lot of terms that I just want to get through. Okay, so for the reason that I mentioned before, when we had that unbalanced data set, accuracy is never, the accuracy of what you're guessing can be misleading. So things break down into true positives, true negatives, false positive, false negative. Whether it's right or wrong in the real world, and whether you guessed it right or wrong, and every linear combination of those four. So things like precision will come up a lot, recall will come up a lot, and then accuracy is the sum. So there's any questions on that? To make things a little bit more complicated, specifically in the classification business, we use this graph a ton. But we have our true positive rate, which is how many times we're getting it right, and our false positive rate is how many times we're getting the negatives wrong. And then we have this pretty graph. And what we're trying to do is the area under this graph is really at the cornerstone of what we want. We want this graph to go straight up and straight across and encompass the entire area of the square if possible. And the closer we get to that, the more accurate our model is. So this encompasses when you get it right, when you get it wrong. Now, caveat with this is it depends on the business case. So your model, if you go back to the cancer example, your model might be much more dangerous to tell someone they don't have cancer and be wrong than tell someone they have cancer and be wrong, right? So even though you're going to want the best performing model, you knowing what you're doing and what the implications of what you're doing, you have to make that decision on where you draw that line, right? So you might not care about this thing just on how many times you get it right. You might say, I want to be absolutely certain that when I tell someone they don't have cancer, they don't have it. As opposed to giving them a false positive of saying, hey, I think you have cancer, go get yourself checked out. And it turns out they didn't. You give them a scare, it's not good news. But if you tell them they're good and they don't get checked out, it could be worse. Right? Like I know I'm using a pretty serious case, but just because this is how good your model is, but you can shift your parameters of your model to be very sensitive on one side, for example, your false positives or your true negatives or however you want. So this might not always be just the best indicator of your model. Any questions? Okay. So let's go back to the code. Okay, so what I've done here is done a lot of data stuff, so all that data feature stuff, I'm not going to show the code because it's lengthy and it's a little too coupled with Python, so here I'm breaking apart the 10s and 20s and the 20s and 30s and doing the one-hot encoding and all that stuff. So we'll just scroll through that. I want to get into the model piece. So feature engineering, we talked about it. Categorical features, so this is all that stuff. Here's where we're seeing what kind of categories and counts. These are all things that help you decide which encoding to use. This is also a public Jupyter notebook, so I'll publish this with my slides so you can go through it yourself and run through the whole thing yourself. This one does not use Azure AutoML, and I'll explain kind of what it's doing and why AutoML can really help us. Extra features, so we put some extra features. So some feature summaries, some charts, all the fun stuff. Now we're building the training sets, we're just slicing data. We're trying to do some undersampling. So just one second, I just want to find the model piece. So model selection. So what we do here, so we build, so what's going on here So because we know that we want categorical supervised learning models, pick some of the popular ones, and then we manually train it, and then we manually validate it, and after 5 or 10 or 15 models, we compare the results. That on its own is what AutoML does really, really, really well. You give it your training set, you give it the column it wants to predict, and then it goes and tries every combination of models under that bucket that it thinks, and then we'll come back and say, hey, out of these 500 models that I picked, here are the top 3 that perform really well. This, as a manual process, can be very difficult. So, for example, here's K and N, right? We learn it, we train it. Sometimes these classifiers or these models have different parameters, different things we've got to tune. So you got to get to know how to use them individually, which is good. But sometimes when you want to do this kind of spread, right? You want to try a whole bunch of things, see what works. It can be very time consuming. So logistic regression, we'll train it, we'll validate it, and then at the end here we'll see some graphs on which one performed. Nice. So I don't want to make you guys dizzy. I apologize. It's a large notebook. Random forest. These are all. Okay, 1 second. Is there any questions thus far while I wait for the? So this is something that we'd see, right? The area of the curve for all the ones we use in this example. Green is the validation set, right? And then blue. Sorry, touch something. Blue is the training set. So from here, you know, depending on which one you look for more, now you're starting to run into the underfitting, overfitting problem. So does anyone know what overfitting, underfitting means? Okay, so I'll explain it for everyone else. So when we run models, if for example, if my model is really good at my training data set, but really poor on my validation of my test, it has a huge bias on the data that I trained it with. That means it's too coupled with how I trained it. And in the real world, if it's not my training data set, it underperforms, right? And then the reverse problem can happen. Or you can be too coupled with the validation set, not the real set. So there's a whole bunch of techniques. There's a whole bunch of techniques we can use, which is kind of out of the scope of this presentation, because I want to get into the ML piece. There's a whole bunch of techniques you can use to fight the bias. Sometimes you need to add more data. Sometimes you need to go back and balance your data better. Sometimes you need to use parameter regularization. There's a whole world after that on how you kind of get your model to perform, depending on what you see here. And the third one missing, which is the test data set, right? And then you start adjusting. So for this data set, let's go back to the slides. Okay. So this is where AutoML comes in. Yep.
Could you throw some light on the ensemble kind of approach?
The ensemble approach? For what specifically?
Like you said, the models.
Yeah. You mean talking about the actual models we use?
Yeah.
There's one specific one you want. I wasn't going to cover the which of the models we use, just because that would have been its own. One second.
So picking up the right model.
Yeah. Oh, yeah. So.
He's talking about the automated machine learning concept in general.
Okay. Yeah. So I'm getting to AutoML and which one we picked in a second. If my screen comes back. There we go. Okay, we're good. So before I show you AutoML, let me just kind of explain what it does. So the way AutoML works, kind of like I hinted at, you have to prepare the data set. So you have to do everything that we talked about, the feature engineering, all the normalization stuff, creating your data set, sampling it, undersampling. You have to do all that work. And then you get to this step. Sorry, there we go. So you get to this step, and so this is the reason why when you guys hear that AutoML is going to replace data scientists, or that it's going to somehow figure everything out on its own, this is kind of why that's going to be really misleading. Because if you give any AutoML the data set that we first saw with the string values and all that stuff, just as is, it'll do some crazy stuff. It will not actually perform in a real world scenario. You still have to understand that it's using the models in the background. It's a tool to help you pick the right model 100%, and it's part of the best practices, but it's not a replacement for the field, or it's not that there's no need of, you just need data engineers and not data scientists. You need to understand kind of how these things work. So what we've done here, what I've done here is I've gone to, now, this is my last slide. So I don't know, I'll finish AutoML and I'll get back to your question, hopefully I've answered it. So this is Azure Machine Learning Studio. There's many ways to plug into this. You can do this directly from a, hopefully my internet's pretty good, but let's go back to the home. So you can do your own notebook directly on it. You can use the AutoML, which I'll showcase in a second, and the designer. I haven't actually used a designer. So the way it works, so when I do AutoML, I'll start it. I have one that I've set, but if I wanted to create it again, I get all the generated, all that work that I did creating the data set, and I can either upload it manually, or because of the storage, I can upload it directly from blob storage, or from a website, or from this one, which is really cool. This is the open source data sets. In this case, let me go back. I took a dump of the CSV file, or the data frame, when everything was done. All the features were finished. We did all the encoding, we normalized all the numerical data, and then I uploaded it here. And and so this is kind of so it takes about 20 minutes to run, depending on the data set, so it can take quite a long time. So this one took 27 minutes and 7 seconds, and then it looks like I tried to run it again for whatever reason after. But here is the models that it generated. So these are very specific, not your typical models. And here is the kind of very under the curve, right? But it went through a whole bunch. It went through a whole bunch, and you can time box it. You can say it. I want you to try everything. I want you to try just the best ones. So if I picked on one, for example, and this is something that SGD, I've never worked with that. I'm not too sure about it. But what it not only gives me the prediction score, it also starts to give you the weights, and it starts giving you the hyperparameters depending on what model is selected. So if you wanted to reproduce this, which is part of the best practices, you take these hyperparameters and it's giving you can deploy it straight. You can go right into Onyx, you can pick it up and use it. Or you can use those exact same hyperparameters, use the data, and then through things like TensorFlow or whatever other open source libraries you want, you can rebuild that exact same model, and you should get these exact same metrics. But what you got here is you got an 88% accuracy, which at the end of the Jupyter Notebook, I think they had like 60 something. So this is where this gets powerful. And then if you wanted to change your features, it's the same thing. You still go through, you still give it that clean data set, and you let it run again. And it might pick completely different models. So this is where you start plugging this in to that experimental phase. So you don't have to manually train all these models yourself, graph them out, and then do all this analysis. Is that okay? Is there any questions on, yeah?
Will this also give us the validation score of the confusion matrix and the area under the curve and the K-fold?
So kind of like visualizations?
Yeah, of all the validations.
So you select one, so this is, So you would have to probably, so this gives you all the visualizations of that model you selected. So I think right now for me, it gave me top 5. If I go back to, let's go to run 1, models. So here I have pages. See, like there's pages of models. So if I click 1, I get the visualizations, but it won't visualize all of them for me. But it will sort them in accuracy order. Yep.
How does AutoML deal with orchestration, and does it scale reversal?
Yeah, it does. So what it does is, so it's going to run, so AutoML is going to run on the data set you give it, right? So you give it the training data set, and it trains. And then you use that model to hit it with your validation set and your testing set. Now, in the times where it's really good with the training set, really bad with, let's say, the real world, so you have bias, right? You're overfitted your data. At that point, you have to kind of go back and be like, it's not going to change the data set for you, right? If it's because it's unbalanced, like I said at 90-10, you just fed it like just a random sample of 90-10, it can't figure out that it needs to go back and get more data. That's what like you have. That's where you're still needed to understand what's going on. But it'll train the best model it can for the data that you give it, and that's it. So you're the one that validates it. You're the one that has to maybe change that training data again. But it just knows what you give it. Does that answer your question? Yeah.
So when you said tested with TensorFlow, can you actually do it in Azure?
So yeah, so in Azure ML you can just do a notebook, right, which is just Python. You can import TensorFlow from there. This you can export. So here you can export the model itself. I forget exactly. I think it was an export. So what you could do is you can export the model yourself, import it into your Jupyter notebook, or any other Python or Scala or whatever you want to use, and then just run that with TensorFlow as you wish. Do the custom import on TensorFlow with that model and then run off with it. Yeah. No other questions? So that was I know I probably went through that fast. That was kind of all the stuff that I had. I really wanted to showcase how we go through any app whatsoever, and then B, how we can use AutoML in any capacity to really solidify our assumptions of what we made, and how difficult it is when you pick selections, when you add features, how kind of time consuming it can be to train all these models, and then they don't work, and then you train some more. This starts heading you into the right direction. If you start seeing AutoML's picking, this subset of models all the time, you kind of know you're in the right neighborhood, and then you go and tweak with it depending on your business case. It has no understanding of the data, right? So if you go back to that cancer situation, just because it's overall more accurate in a certain way, you might decide that, hey, you know what, I actually don't care about false positives, right? I care about false negatives. I care about the fact that when I tell you don't have cancer, that's the case that I want to be absolutely certain on, like, I do not do that. Not so much that it's obviously not great, but like that I overdo it on the other side. So, yep.
So is there a model repo where you can actually publish all these things?
So this is, yeah, so the AutoML has all your models saved, but if you're looking to productionalize this, you would have to follow the same kind of production like MLOps standards, where you would upload this to whatever repo you used your models in, and then plug that in. Yeah.
Once you import your Jupyter notebook,
Yep.
and you click on designer, will that convert your notebook into a designer drag and drop model?
I haven't used the designer, so I'm not too sure what it does, but I usually just work with the notebooks. Let's find out what it does. So it just gives you, I don't know why it's this is like, I have no notebooks here because my Jupyter notebook is running from my local, like this one here is running just from my local host that I've installed. But you can definitely put it up here. I'm not too sure what the designer tab does. I just stay with the Jupyter notebooks and the AutoML. Yeah. Any other questions? Yep.
What visualizations do you have? Do you have the explanation of the variables in terms of importance?
The variables of importance, you talking about the, like when model evaluation? Yeah, I have this on the slides, and I will be sending this slide deck out, so like this stuff. Is this what you're doing? So I have this stuff in the slide. This will be available when they send out the email with all the presentations, so you can look back at it, and there's footnotes on what sources I've used for these definitions.
No, actually I was asking about does Azure learning automated have the explanation of the variables?
Oh, I see. It doesn't, but it does in its documentation. So you're talking about now that I've run it. So yeah, I got it. So so now I've run it, for example, and I go to my models, and they say, okay, this one has 88%. This one's good. I'm confused on run metrics. What does precision score macro mean?
Right. What is the explanation there? Does that have anything?
So this one, this doesn't have any explanations on this, but on the documentation, so if I was to go, they should have it on their wiki page. So I go, sorry guys. So here's where they would have all that explanation on the documentation side. Yep.
Are there some kind of REST APIs available for AutoML?
Yeah, there should be. So there's one way, I know the Azure Machine Learning Studio, which is another product, has a way that you can put whatever you want in there and it'll immediately create REST endpoints when you publish it. That's probably what I would use because that's been set up for that environment. AutoML on its own might have something, but I would recommend to put it into Microsoft's Visual's Artificial Machine Learning Studio if you're going to actually want to do endpoints. That'll do all your OAuth and all that stuff right out of the box. Okay. Well, thanks, guys. If I have any questions, I'm here, or I'll just be there behind you guys. Thanks for spending some time and understanding AutoML. I highly recommend you guys try this stuff out. As I mentioned, one really cool thing is, for example, if we wanted to create a new experiment, if we don't want to do all that work of feature engineering first, we just want to check this out. You can easily just create a data set from these open data sets. Some of these are already prepared for you. So there's a whole bunch. For example, diabetes comes up. These are publicly available data sets that are used for things like Kaggle. They're used for a whole bunch of. Even if you just want to try to find some insights, one of the things that we get asked a lot is a client comes to us, kind of dumps us their data, and they tell us, show me some cool stuff in my data, kind of show me some insights. They're not really, like in this example, we had a case where we were asked to do something specific. So a lot of the time they just throw your data at you and be like, hey, what can you find? Can you find that 40% of my loyalty customers are in this region, or that they shop between this and this hour, or that they usually buy this type of basket? And so when you don't have a direction on where to go, you spend more time in that data engineering world, and this is kind of what these data sets can prepare you for. So you can kind of like pull these out, take a look at them, massage the data with whatever tools you like, and try to find some correlation between certain columns, and then build whatever models you want on top of that to verify your result. Maybe you can predict successfully that if someone bought 2 coffees, they're going to buy 2 coffees the next Friday, or whatever you kind of want to do. So this is a really cool tool to experiment. I know another really good source is Kaggle.io. .com, I forget which the ending is. That's where like a whole bunch of people throw out their data, and you have a whole bunch of data scientists like massaging it together. You can do groups, and there's even like prizes for some of this stuff. So it's really cool if you're just trying to get into the field. And you want to stay away from a little bit of the math. It's really hard to just look at this glob of data and try to make sense of it. But the more times you kind of do it, there's things you kind of start picking out. So these are all tools to kind of accelerate that process. Okay, thanks guys.
Yeah, so I can show you. So studio. Yeah, so
بعدين نروح البيت نروح على الجيم بعد ارجع من الجيم عندي درس بعد الدرس
So AutoML has all the tools that you want to do, so you can do like data massage. If you know you want to use data, it's all those AutoML is a bit different. AutoML it tells you you just rotate the data and it'll tell you if you want me to predict this column in your data. I found that these boxes are better than these boxes. UML is you do all that, but then you decide, okay, I want this one. So that's why you can use the conjunction. The main difference is UML, it's not telling you what model to use, you're telling it. And with AutoML, the only thing it's doing is giving you the right data and all